not even do the entire part 3. I'll show you. So I was estimating that, and yeah, my thing's not charged up, so I'm carrying around a battery pack. I was estimating that we would get done early, but don't tell anybody, okay? So we're going to continue on this topic of thermodynamics, which the thing about I've run into in the past with high school students or students who had chemistry in high school is that they don't hit this very hard, or if they do hit this idea of, remember Friday we said it's kind of tossing energy back and forth, and it's kind of a hard thing to grasp. So just kind of, keep up with it and you'll do great. So actually we talked about this on Friday. The idea that you could have a cup of water and a bathtub of water. The thing of interest is the water. You could have two different amounts of water, the same temperature, and you guys told me the bathtub would have more energy, more thermal energy. Remember, thermal energy contained by these chunks of water is different than temperature, because I could put a temperature probe in both of those and it would read the same. The thermal energy associated with the junk in the bathtub, the water in the bathtub, is more. So then you guys told me that not only the temperature, what your thermometer says, but it's the amount that says how much thermal energy an object has. So that's cool. There's one more thing that you need to say how much thermal energy an object has, whether that's water or a pen or a thing of metal or something, and that is actually what we call its specific heat. Specific heat or specific heat capacity. And we'll be talking more about that in this part. Okay, the C sub P. Okay, C sub P, that is specific heat. That's supposed to be C, not a B. Okay, and guess what? This is going to be a constant. So you know what we do with constants. We don't generally start with them, okay? It's a constant and you look it up. Or you're given enough information to calculate it. Okay, so the specific heat. The water has a specific heat, metal has a specific heat, plastic has a specific heat. So specific heat or specific heat capacity, that thing you look up, that C sub P, okay, oops, that specific heat, it has units of energy per gram degrees Celsius, and usually it's joules is the energy, joules per gram degrees Celsius. Okay, we've been working a lot with unpacking things and making sure our units cancel and dimensional analysis and all that. Okay, so if you look at kind of the definition of what specific heat is, it's kind of fun. It's actually, this looks familiar. You take 1 gram of the material, exactly 1 gram of the material, and you heat it up from usually 14.5 degrees Celsius to 15.5 degrees Celsius. So like this says, and we're going to call this delta T, the change in temperature is 1.0, degrees Celsius. Okay, so that actually is the specific heat. The energy you need to raise 1 gram of that material up 1 degree Celsius, so you look it up. So there are different ways of expressing that. Notice that, and it's kind of cool, we talked, no pun intended, we talked about the Celsius temperature and the Kelvin temperature. They're both metric. Isn't that awesome? The Kelvin scale is more awesome because it's 0 is really means something. But do you remember that they actually, step by step, are equal to the same magnitude? Okay, so related to that then, if you have 1 step change in a degree Celsius, it's the same as 1 step change in the Kelvin scale. So that's significant. Okay. So they're both metric and kind of, I repeat this slide later on, but 1 unit is the same on either scale. And that's going to be a wonderful thing. It will make our lives easier anyway. So here are some things that you might be working with here or there. It's an assortment of metals, an assortment of nonmetals. These are all elements. And this is how much energy you would have to zap 1 gram of them to raise them up 1 degree Celsius. This is their specific heats. So I didn't mention it, but you can kind of see up here at the top that here we have units of, if you see something raised to the -1 power, negative anything power, it's in the denominator. So notice that this actually is the same thing as joules per gram raised to the -1st, puts grams in the bottom. Celsius raised to the -1st, puts degrees Celsius also in the bottom. Okay, so just to kind of make sure we're all on the same track. So to get you thinking about this, this means, for instance, can you see that magnesium, let's pick on magnesium, it's got a big number. It means you have to zap it with 1.024 joules of energy to raise 1 gram, 1 degree Celsius. Check out tellurium. Tellurium. It's pretty easy to heat up. You only have to zap it with, that's joules of energy. You only have to zap 1 gram of tellurium, 0.202 joules to raise it up 1 degree Celsius. This is an indication of kind of how easy or stubborn they are to heat up. It's a physical property of that metal. Here are some other specific heats. Notice that it's joules per gram, not degrees Celsius, but Kelvin, and they're actually interchangeable. So one of the ones, and I have it coming up at a table, or is it here, you are going to want to memorize the specific heat for water. Notice this is kind of a fun thing if you think about it. Here we have water in its 3 different forms, solid, liquid, and gas. And notice that it has 3 different specific heats. Is that not fun or what? Simply means that you need to, as far as how much energy you need to zap it with, 1 gram of it, to raise it 1 degree Celsius, it's different.
So I have to memorize all 3 of those?
No, just this one. Oops. Yep, there's my arrow. I thought it was. So, yep, just this one. For liquid water, the 4.184. Specifically, remember that means 4.184, joules per gram degrees Celsius. That's the specific heat of liquid water. Yeah. Does that, I won't ask it in the form of a question. I'll just tell you, we ran into that same constant on Friday's lecture. We said that with regard to energy, that actually is the smoking gun, the link between units of calories and joules. Okay, 1 calorie is exactly equal to 4.184 joules. That's kind of fun. I'm using that word too much right now. So another thing, does that almost look like an outlier? You know, in science, we're always looking at numbers, blah, 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 looking at high numbers and low numbers. Doesn't 4.184 joules per gram degree Celsius look like a high number? And it is. It simply means that, to me, the way I look at it is it's stubborn. You have to add a lot of joules of energy in order to raise it up 1 degree Celsius. The other thing, though, and this is the specific heat capacity, this is the capacity part of it. Once you have water heated up to a certain temperature, it retains its thermal energy. Okay, so it has a lot of energy. So it's hard to see the last column, but the last column is the specific heat of those same things. Now, not in per gram, but per mole of that substance. So that could be helpful. And we know that we could, and I'm not going to make you do it, I'm not going to put you on the spot, but you guys know that we could use the molar mass of water to go back and forth between joules per gram Kelvin and joules per mole Kelvin. I bet I could turn you loose and you'd knock that out factor label. Okay, so it's the same thing. Okay. So these are some kind of, kind of empirical sort of things just to kind of get you thinking. So I'm going to kind of over here at the edge diagram what the situation is. Notice that we have 2 elements. We have copper and we have aluminum. And so here will be my, I'll make squares. We'll hopefully kind of add some more dimension in your own mind. So this is my copper, and this is my aluminum. And notice that in these two scenarios, we are going to dump 500 joules. I literally think of zapping them. Zap it with energy, 500 joules in each case. The other thing, and we know mass makes a difference because when we consider a cup of water versus a bathtub of water, mass makes a difference. Notice that just to kind of remove that, whatever, there's the same mass. So here's the deal. Just looking at the specific heats are these two numbers. So for copper, it's 0.385, and for aluminum, it's 0.897. 0.897, more stubborn to heat up. You have to put more energy to raise it 1 degree Celsius. So can you see where the final temperature, pumping them with the same amount of energy, the final temperature of the metal with the same mass, with the higher specific heat is less. Okay, that's just kind of empirically looking at it. So actually, we're going to talk about how you can calculate that final temperature. Okay? Yeah?
I had a question, because you know how you told us never to do on one ratio? How would you do it since there's three? There's joules, grams, and Celsius.
I think I know your question, and I would say, and it's maybe coming up, and I'm glad you brought that up, I really don't like this convention, J/G/degrees Celsius. And when I unpack this, and I don't know if this will answer your question, but actually, when we use this, any specific heat in a problem, this one for copper would be 0.385 joules per gram, and that's my little multiplication, dot degrees Celsius. Does that make sense? Yeah, I don't know why they do that. I really don't like this way, but they mean the same thing. Don't mind me. Some guy thought of that. No offense. Okay, you're right though. Okay, so now this is a little bit different. Okay, notice that we have the same mass, and of course we have copper, aluminum, same deal, and of course we have the lower specific heat and the higher specific heat. But in this case, and I'll go ahead and draw little boxes over here just to kind of emphasize, we're eyeballing this basically. We're going to crunch numbers here in a minute. But this is my copper, and this is my aluminum. Notice we have the same mass in both cases. We are going to zap them with a question mark. And you can see what energy we zap them with. Zap them with a question mark, but that's kind of our variable here. Notice that in both cases we want to have the same, I'm going to say heat to same. I'll just put it in the middle there. Heat to same temperature. Okay? That's kind of the process of what we have going on. So with all that in mind, again, if we kind of pick on aluminum with the higher specific heat, can you see where we can get to the same final temperature, 50 degrees Celsius, but check out what we got to pump in. Notice you see the first look at what variable we're going to use for that, this question mark, this heat, this energy, either coming in or going. Okay, we're going to actually use Q for that. Okay, so does that kind of make sense? It's got a higher specific heat. It's a physical property of that metal, of aluminum, compared to copper. Okay, and we can actually calculate those numbers. So yeah, I know all my slides tend to have that goofy three-way sort of ratio. You're like, really? But the more you work these problems, you'll be like, oh yeah, they really mean energy for either mass or moles, and then also in the denominator is the temperature, degrees Celsius or Kelvin. So memorize it for water. The specific heat for liquid water, right? Okay, is 4.184 joules per gram degrees Celsius. And remember, degrees Celsius and Kelvin are interchangeable, actually. Or in units of English energy, 1.00 calories per gram unit Kelvin. All right, so in general chemistry, we don't do much with, this reminds me of physics. This is basically a relation, it's an equation. And I don't do much with equations that you can kind of plug in, but that's what this is, okay? This is to me, just kind of reminds me of physics. Basically, we're talking about the relationship. If you have a blob, we've been talking a lot about blobs of stuff, okay? Here's my little cube, okay? That cube, the stuff in there that has a certain amount of energy, the stuff has a certain mass. The stuff has we can look up its specific heat. Okay, now, Q and T. Q, and I should say delta T. I want you to, and this is a physical science thing. I want you guys to get used to, if you ever see this Greek letter delta, that means change in. And it's funny because, I've been teaching this, or I've been kind of in physical science for a while now. When I see that delta, that triangle, I'll say the word change in, okay, sometimes. So delta T is change in temperature. So kind of get that. That's here to stay, actually. So this is the change in temperature. It's right here. Temperature change. And Q is the change in energy. Okay, so Q is the change in energy. Energy could either be added to it, so this is Q, Q added. If you're a visual sort of person, like I am, or this is Q released. And both, that's supposed to be released. And both scenarios are important. Okay, so basically we have an object either oozing energy or accepting energy. We have that object's mass, its specific heat, and the change in temperature we observe. That's it. Okay. I almost think it should be like a rap song. Q is equal to M, C sub P, delta T. Okay. So this gets back to kind of what Chelsea said. We're going to be real careful with how we set up our problem. In some physics teachers don't emphasize the unit thing like I do, but you're going to have to put units and show cancels-nations and everything. Okay, so what this says is, I'll just kind of show you how this works, just kind of plugging in some variables. Do you see if we have, I'm going to kind of set these three terms up beside them. Our mass needs to be actually in grams, and I'm going to put it over 1, and you'll see why. So that's my mass term. The specific heat, we said, let's go with joules per gram degrees Celsius. That's what we look up. That's the specific heat. And of course, the change in temperature, a very good change in temperature, is what its Celsius temperature changes as. So do you see how if we set up the mass, the specific heat, and the delta T, it's a wonderful thing how things cancel. I can't overemphasize that. So grams cancel. Okay, and degrees Celsius cancel, and we're left with units of joules. So as you work these problems, I'm going to need to see all of that. And the joules should make you smile, because joules are great for Q. What's Q? Change in energy. Remember, Q is the coming in or squiggling out energy. Okay. So actually, delta T is a little subtraction problem in and of itself. I said anytime you see deltas, that's change in, and changes are always final state, and from the final state, you subtract the initial state, and it's almost backwards. It's final minus initial, always. That's a standard, okay? So it's a little subtraction problem in and of itself. So here's the deal. So if something's cooling off, you can't see it, but the little squiggles are like, going off like that. Okay. If something's cooling off, then that means its final temperature is less than its initial temperature. Okay, so that means the delta T, the little subtraction you're going to get, is actually negative. Okay. If your final temperature is less, it's cooling off, your delta T term is going to be negative, and that's awesome. Of those three terms that make your Q, the mass, it's never going to be negative. Your specific heat is never going to be negative. Your delta T's can be negative or positive. So actually I don't want to say a tricky part, but that's an important part of doing thermodynamic problems, is making sure you keep your sign. Okay, be bold, okay? If the thing is picking up a squiggle, picking up energy, right? Okay, so that means the final temperature is greater than the initial temperature, so when you do the subtraction, you'll get a positive delta T, and that makes your Q positive. All right, so just one more time. It's funny because, well, not really funny, but when you look up the specific heats for things, if it's given per degrees Celsius or per change in Kelvin unit, I'm fine. You can actually use them interchangeably. What I think is funny is I don't make you do any sort of factor label because they're all the same thing. Okay, so I kind of said as much this whole thing. I said that your changes in temperatures can be positive or negative. It's cooling down, it's going to be, and I always have to think through this. Cooling down, it's going to be negative. If it's heating up, it's going to be positive. And then that will drive the sign of your Q. Okay. So the two possibilities we have is, and I'll just kind of re-emphasize this. Here's my little box of stuff. Okay. Energy being added. Okay. Your final temperature will be greater. Okay. And your Q will be positive. Down here we have the thing, energy is being released. Now the thing about thermodynamic problems is that, see that little E going in or that little E coming out? One of the things we're going to talk about more on Wednesday is that it can't just come from nowhere, and it doesn't just go to nowhere. Okay, the conservation of energy, it needs to be tracked somehow. All right, so let's do one. So it looks like this. I'm going to go ahead and diagram this. These really, for people who hate story problems, to me these really kind of look like story problems. But it's okay. It's all good. And so what I like to do is, like you've seen me do before, just kind of take the stuff out of the problem and put it on a goofy picture next to it. Okay, so even without writing anything else down, I'm going to write what I've got. So here it says mass of the water is 37.7 grams. Okay, let's see. Originally at 52.0 degrees Celsius, cooled down to 5.2 degrees Celsius. So I'm going to write T sub I. What's my T sub I? What's my initial temperature?
52.
Very good. 52. What is my final temperature?
5.2.
Perfect. 5.2. Excellent. Do you see where we could, and it's knocked out on my build, so I'm not going to do it here, but do you see where we can do subtraction and get delta T? Get delta T from here? Awesome. Let's see. So that's all the stuff they give me. So is the water, how many people think the water is losing energy? Me too. Cool. Let's do a little squiggle. Okay, I can either do a Q or an E. I'll put a Q here. The change in thermal energy. Energy's gone. Okay, so actually to calculate Q, we're going to just kind of set it up. Q is equal to MC sub P delta T. And we said we can get the delta T from here. The mass was given. How about this specific heat? Yep, 4.184 joules per gram degree Celsius. So you have to have that memorized. Exactly. So here in so much is what I kind of picked out on the other slide. Notice we haven't done a lot of subtraction. We don't do a lot of subtraction, it seems like, in chemistry. But can you see where, since we're subtracting, we count decimals, and we have 1 decimal in each of those, so we're allowed to carry 1 decimal. And don't be caught by this, because I'm sure it's caught me before too. But deltas are always final minus initial. Okay, so the final minus the initial. Because it seems like we always want to kind of go initial minus final, but it's final minus the initial. Okay. So here it is. You can kind of see the ratio already start. There's no really first term to start with. This is just kind of, this is what it kind of reminds me of a physics problem, where you have a relationship between Q and MC sub P delta T. It happens to be that Q is the product of those 3 terms. So we just line them up. But notice that in your solutions too, you need to include units. Because including units, like we looked at before, grams will cancel and degrees Celsius will cancel. And don't lose the sign, okay? Okay, so we'd say the change in thermal energy, Q, is equal to negative, and you wouldn't have to pack it up in scientific notation. But I did. Negative 7.8. Notice I'm keeping 3 significant figures because I have 3 significant figures in the mass and the temperature. We have 4 sig figs in that specific heat, but we have to go with fewest. Now, unless it's said, you don't have to do this last step. But there are times when it's nice to get Q in terms of not joules, but kilojoules. Okay? It's just a convenient thing. In this case, if you left it as joules, you'd be fine. Any questions about that? So that's the little squiggle escaping, but it went somewhere. Okay. So a little bit of semantics here. The next slide is going to talk to you a little bit about, well, you'll see, semantics. It's important that you say Q is equal to negative 7.38 kilojoules or negative 7.38 times 10 to the 3rd joules. It is possible, if you were going to say, use the words, if you use the words energy is lost, I'd see if this makes sense. I bet you by this. If you literally use the words energy was lost, you are already saying Q is negative. Okay? So it's possible then, if you do that, you wouldn't say negative 7.38 kilojoules of energy was lost. Okay? It's implied there. Does that make sense? Okay.
So if that number wasn't negative, would energy have been?
Yes, very good. Mm-hmm. Very good, yes. So I have screenshots of these, and I'll try to get them out there so you can have access to them. But there are several problems listed at the end of this part, and I want you to do these problems for Wednesday. Problems 7.1 and 7.2. And they're so fun, I'll show you. But there's some twist to them, so I was glad to take just a few minutes to kind of, if you'll indulge me, to show you kind of how these kind of take a different form sometimes. So here's 7.1. Let me kind of clean it up here. Okay, so there's 2 parts to this one, and actually they are independent problems. So in this one, it's dealing with water. They give you the initial and the final temperature of the water. Of course, you can come up with delta T. It's always final minus initial. You got that stuff there. Okay. And I guess there's not really too many hitches here. It's like we just did, isn't it? You can either look up specific heat of water. I guess here's the hitch. They don't give you the mass of the water, but they do give you the volume of the water. So this class is very accumulative. And so since you're given liters of water, the 9.25 liters of water, you're going to have known what's the density of water. It's that nice, clean 1.00 grams per 1 milliliter. So you're going to have to plug that in. Okay, that's why I say get mass from that volume, 9.25, liters and the density of water. That's my hint. The next one, it uses aluminum. There's my little chunk of aluminum. And notice they give you the specific heat of aluminum. They give you mass in kilograms. Don't be caught off guard. You're going to want to convert that from kilograms to grams to use it, okay? The specific heat, I say you could look it up, or they give it in the problem. You don't have to memorize the specific heat of aluminum, okay? I would give it to you either in the problem or a table. So, yeah. Notice here, do they give you an initial temperature for B? If you're like me, you have to read it several times. I think sometimes when we're starting out in a new discipline, we're like, I don't want to read it again. But you have to. Go ahead.
Wouldn't delta T just be 33.5?
What's that?
Wouldn't delta T just be 33.5?
It is. It is. Delta T is just 33.5. But notice it says that it's a decrease in temperature. Yep. Yep. Yeah, very good. So you have to be able to kind of be flexible. Any questions about that? Yeah. The next one, though, there's all sorts of variations, which is good, I think. There's also two parts to the second problem. In this one, they give you, it's water again, they give you the mass, they give you the initial temperature. Notice that squiggle in. They're telling you Q, basically. They're saying we're going to add energy, okay, but they're not giving you the final temperature. Okay, so they don't give you the final temperature. They give you Q, they give you M straight out, mass of this water, and you know the specific heat of water, 4.184 joules per gram degree Celsius. So with all that, you can actually solve for delta T, can't you? And once you have delta T is T sub F minus T sub I. You have the initial temperature. The final temperature is delta T plus T sub I. Okay? It's a very common, very common, it's not really a twist, but it's out there. Any questions about this? So yeah, if you're like me, it has to kind of sink in. The second one, the B part, okay, now it's dealing with not water, but platinum. It gives you the specific heat of platinum. It gives you the mass in kilograms. Remember to convert those to grams. And it gives you the Q again. It says that it's giving off 1.05 kilocalories of energy. So the T sub F is going to be less than the T sub I, isn't it? So you're going to have a similar approach. You have Q, you have M, you have C sub P, you don't have delta T. You can knock out delta T, and once you have delta T, remember the relationship between delta T and the final and initial temperatures. Some problems go at the other one, the final temperature instead of the initial temperature. These are all both going after the final temperature. Okay? So these will be posted out there in case you want to use them. And see, I told you you're getting out early. Don't get used to it. Sure. Yes, I do. I do. Thank you, Lance. Come on.
So on the problem before with that temperature, we were just going to focus on where the changes, the decrease.
Which one?
The problem before.
The B?
No, the last one.
Oh, go back?
Yeah.
Okay. This one?
Yeah, where it says the decrease, like Matthew was saying. So can we just plug that in for change?
Would it be plugging it
T?
in negative 33.5 or positive?
For the B, that would be negative. Yeah.
So when we plug in the temperature, we put in negative 33.5?
This one is where you're given the delta T, yeah, the delta T like I have up there.
Yeah.
Yeah, I just want to make sure I tell you right.
Okay.
Yeah, the delta T like I have up here is negative
Okay.
33.5. And it would be because it's final minus initial and the final is less. So.
Yeah, the word decrease threw me off, so I didn't know if you had to do something. Okay, I get it, I think.
Yeah.
It's
So
not
whatever
always-
says decrease in temperature, it's always negative, right? Or no?
We're gonna mix it up and look at actually a system as two objects, something gaining and something losing. And I just don't want to necessarily make that blanket statement.
Okay.
So, and these it is.